Good morning, everyone. My name is Zhou Tian, and I'm honored to present our work titled Beyond Symmetry, a novel asymmetric interaction strategy for immersive VR-based mirror therapy. Let's start with the background. Stroke has become a significant global burden. According to the World Stroke Organization, by 2025, stroke is projected to be the second leading cause of death and the third leading cause of disability worldwide among non-communicable diseases. Crucially, 89% of this burden falls on low and middle-income countries. Post-stroke survivors face a long and arduous journey. They require extensive training to recover motor function, such as overcoming hemiparetic and reintegrate into society. However, current rehabilitation faces a conflict: the massive demand for rehabilitation versus limited medical resources. This often forces patients, families, and medical staff into crowded environments with repetitive training. For patients, the high cost, long duration, and sheer burden of repetitive movements are significant psychological burdens, especially in the early flaccid stage of hemiparesis. Patients often have to use their unaffected limb or rely on others to move their affected limb during device-assisted training, as shown in the figure. This passive training often provides more psychological comfort than physical gain, leading to low compliance when progress is slow. To address these issues, mirror therapy, or MT, was introduced. By using a mirror reflection, patients see their affected limb moving normally, which stimulates neuroplasticity. However, physical mirrors have limited fields of view and immersion. Therefore, researchers migrated this therapy to virtual reality, abbreviated as VRMT, to enhance neural stimulation. VRMT offers great benefits. It creates diverse, immersive environments that boost patient engagement. By rendering a virtual model of the affected limb from a first-person perspective, it activates the mirror neural system. As shown in the right figure, the prevailing design follows a symmetric interaction paradigm, mirroring the movement of the unaffected limb about the body's midline. But we identify critical issues with this strict symmetry. Specifically, regarding arm abduction, a vital eccentric movement for recovery, we found it's rarely trained in traditional mirror therapy, because the patient's body often blocks the mirror reflection during large movements. When we transfer this to VR, symmetric abduction often causes the controllers to exit the effective training area, or ETA, of consumer-grade headsets. This leads to tracking loss and motion stuttering. While adding external sensors could solve this, it increases cost and setup complexity, contradicting the goal of accessibility. As seen in the right image, our previous high-end system, using HTC Vive and Leap Motion, was clinically effective, but was eventually shelved in hospitals due to these complexities. This brings us to our motivation. Given the vast number of stroke patients, we believe rehabilitation system must be accessible and affordable. Therefore, we propose a software-based interaction solution to solve the ETA limitation without adding hardware. Our setup is simple: a standalone consumer-grade VR headset and a tablet for monitoring via local area network. Inspired by hand redirection techniques used to reduce user frustration, we developed an asymmetric interaction strategy. The core idea is simple. We constrain the control of the unaffected limb to always stay within the headset's tracking area, while the virtual affected limb performs the full range of motion. Here's the algorithm. For flexion, we used a fixed offset equal to shoulder width. For abduction, we apply a 2-to-1 scaling offset. This means the patient only needs to move their unaffected forearm within a small range to drive the virtual affected arm to complete a full abduction. Referring to the animations, let's look closer at the mechanism. In these visuals, the left hand represents the patient's unaffected limb, which is hidden during actual training. The right hand represents the affected limb, rendered via different mapping strategies. Please compare the top right and top left figures. The top right shows the traditional symmetric mode, where the hands move symmetrically with respect to the body's midline. In contrast, the top left demonstrates our symmetric mode. Crucially, observe the movement during abduction to the right. In the asymmetric mode, the physical left hand and the virtual right hand move in the same direction. Furthermore, you can clearly see that the virtual right hand covers a much wider range of motion than the physical left hand. This visually demonstrates the 2-to-1 scaling offset in action, achieving a full range of virtual movement with only limited physical input. Our therapeutic rationale is that the efficacy of VRMT comes from mirror neuron activation, triggered by observing the movement, not by the physical symmetry of the hands. As long as the patient observes and imagines the movement, the neural pathway is activated. To validate our system, we conducted 2 studies. First, the user experience study. We recruited 10 healthy participants and 10 stroke patients. They tried both symmetric and asymmetric modes in a randomized order, followed by questionnaires and interviews. The results showed that the asymmetric mode received significantly higher ratings for smoothness and usability. Interestingly, stroke patients rated the improvement even higher than healthy participants. Our interviews revealed that while some healthy users found the asymmetric mode too easy and preferred the challenge of symmetric mode, patients strongly preferred the smoother, frustration-free experience of the asymmetric design. Second, the clinical efficacy study. We conducted a randomized controlled trial with 31 participants divided into 3 groups: control group, symmetric VRMT group, and asymmetric VRMT group. Before and after 3 weeks of training, we assessed them using the Barthel Index, Fugl-Meyer Assessment for Upper Limb, also known as FMUE, and Wolf Motor Function Test. The results indicated that both VRMT groups showed significant improvements compared to control group. Most importantly, the therapeutic outcomes of the asymmetric group were comparable to the symmetric group, proving that strict physical symmetry is not required for clinical success. In conclusion, while we acknowledge certain limitations in our study, such as the sample size and fixed difficulty parameters, our findings provide a strong direction for future rehabilitation design. This work proposes asymmetric VRMT to return mirror therapy to its essence, mirror neuron activation. By breaking the shackles of symmetric interaction, we successfully resolved hardware tracking limitations through software design, achieving a smoother user experience with clinical outcomes comparable to traditional approaches. We hope this work encourages designers to move beyond strict symmetry and develop more accessible systems based on affordable hardware. Ultimately, our goal is to help bridge the gap in healthcare resources and empower patients to recover in their own homes. Thank you for your attention.